Hello, chemistry students. This is part two of our polarity and bonding slide deck, and we are talking today about the polarity of intramolecular bonds. But before we start, put this on pause, get your chem helper, a whiteboard, a marker, an eraser, and you may even want a calculator for this lecture. All right, so first let's talk about polarity and what that actually means. Whenever I think about polarity, I tend to think about the poles of the Earth. We have a North Pole and we have a South Pole. They are on opposite sides of the globe. And that's what polarity is. It means that you have an uneven distribution of positive and negative charges. And so the positive things might be on one side of the globe and the negative things would be on the other side. It's kind of the same thing with a magnet. Magnets also have poles, and that's what you see on the picture on the right, where you've got positive and negative ends of the magnet, and they are going to attract and form the pattern of the iron filings that are surrounded it. So magnets and our globe both are things that have poles. We have negative or opposite sides. So polarity means opposites. One thing that you're going to be able to do by the end of this lecture is write out by heart the definition of polarity. Polarity is simply an uneven distribution of positive and negative charges. So that kind of means that like you have all of your positive particles on one side and all of your negative particles on the other, instead of them being spread out nice and evenly. For instance, let's take a look at this hydrogen atom. You can see that we have our nucleus in the center with the orange and the blue circles, and then our electron is the purple circle that's in the energy level on the outside. But what happens if we place a charged plate, a positively charged plate, next to this atom? Well, notice what happens. Here in red, we have our charged plate, we've got positive charges, and look at which particle is attracted to it. It's the purple negatively charged electron. And look at what's being repelled, the nucleus, because all nuclei have a positive charge. And so it's going to affect not only the charge, like the separation of charges, but it's also going to affect the shape. So now we don't have that nice round even shape. We've got more of like an egg shape here. All right, so what happens to the distribution of positive and negative charge when we put a positively charged plate next to the atom? Go ahead and pause this, write the answer on your whiteboard. Okay, here's your answer. The negatively charged electrons move toward the positive plate while the nucleus is repelled because the nucleus has a positive charge and like charges repel. The charges become unevenly distributed. Okay, go ahead, pause this, and see if you can write the definition of polarity. All right, polarity is an uneven distribution of positive and negative charges. That's something that you have to memorize. Polarity is an uneven distribution of positive and negative charges. Atoms are not the only things that can become polarized. However, molecules also can become polarized. So remember, polarity, an uneven distribution of positive and negative charges. Say it with me. Polarity, an uneven distribution of positive and negative charges. So let's take a look at two examples of molecules. Our first example is on the left. This is a non-polar oxygen molecule. The reason why it's non-polar is because the oxygen molecule is made up of two atoms of the same element, two oxygen atoms, and they share electrons equally. So if you have an equal distribution, then that means that your molecule is not going to be polar. But if you look at the example of the molecule that we have on the right, this is the hydrogen fluoride molecule where you have a hydrogen sharing electrons with a fluorine. Well, the fluorine is going to pull the electrons toward it, making an uneven distribution of positive and negative charges. When fluorine pulls electrons toward it, it's going to leave the hydrogen side of the molecules being more positive, while the fluoride part of the molecule becomes more negative. And I just want to call your attention here to our to our symbols. So this is just kind of like an S that's closed at the bottom, I guess is probably the best way to say it. But this is something that's called a partial charge. So when fluorine draws electrons toward it, it makes hydrogen partially positive and it makes fluorine partially negative. Why does this matter, do you ask? Because hydrogen is not donating its electrons to fluorine. If it were, then hydrogen would be positive and fluorine would be negative, just like in an ionic compound. But that's not what's happening. Hydrogen isn't donating its electron, it's just letting fluorine borrow it for a little bit. So that's why we say that it has a partial positive charge. Another way to show the direction in which electrons are being pulled is by using this fancy arrow that we have down here at the bottom. So notice that like this side here is like a plus sign. That means that that's the place that the electrons are leaving from. And then the part that actually has the tip of the arrow is showing us where the electrons are spending most of their time. All right. So a molecule's polarity is affected by the electronegativity. Remember that vocabulary word from the periodic table unit? It's affected by the electronegativity of the atoms that it's composed of. And just as a reminder, electronegativity is simply how strongly an atom of one element attracts electrons from another. So the more an atom is able to pull electrons toward it, the higher the electronegativity value is. And if you look at this periodic table, the darker the square, the more electronegative the atom is going to be. We can see right away that fluorine is the darkest colored square and it has the highest electronegativity value, while down here at the bottom by our alkali metals over here, cesium, francium, those are the least electronegative atoms. And that should make sense to you because those are metals. Metals don't want to gain electrons. They want to lose their electrons. So of course they're going to have very low electronegativity values. All right, now I know that you can't drag your dot, but I just want you to write on your whiteboard, how does electronegativity change across a period? So remember that periods are moving east-west, or west-east, I guess, like left to right on the periodic table. They're moving from from metals all the way over to non-metals. So what's happening to electronegativity? If you chose increases, then you would be absolutely correct. Okay, next one. Next one, please. Okay. Metals are more electronegative than nonmetals. Is this true or false? Well, folks, the answer to this would be false. Metals are less electronegative than nonmetals because metals want to lose their electrons to achieve a full valence shell, while nonmetals want to gain electrons in order to achieve a full valence shell. Okay, now let's see if you remember. Can you write down the name of the element that has the highest electronegativity value here? If you picked fluorine, you are correct. Yes, that is the one that has the highest electronegativity value. Oh, hey, write the definition of polarity. Put this on pause and see if you can write it down on your whiteboard. All right, if you put down an uneven distribution of positive and negative charge, then you got it correct. All right. a little bit more on electronegativity. So remember that the definition of electronegativity is how strongly an atom of one element attracts electrons from another element. Remember that very electronegative atoms are going to pull electrons toward it, and it's going to have a partial negative charge, and that's what we have right here. So fluorine is the most electronegative element on the periodic table, so it's always going to win. It's always going to pull electrons toward it. But remember, it's only a partial negative charge because it's not taking the electron from hydrogen, it's just borrowing it for a little while. And likewise, hydrogen then is going to have a partial positive charge. Why? Because fluorine is borrowing its electron for a lot of the time. Hydrogen isn't giving it its electron, it's just, lending it out for a little bit. All right, so take a look at the periodic table that I have here at the bottom, and which has a higher electronegativity value. Is that hydrogen or is it oxygen? Well, if you said oxygen, then you would be correct. And which attracts electrons better, hydrogen or oxygen? This would be oxygen, because if oxygen has a higher electronegativity, that means it's attracting electrons better than hydrogen does. So make sure that you keep this stuff in mind for just a moment. So what we're going to do is make some water. So the chemical formula for water is H2O. We said on the last slide that hydrogen has a lesser electronegativity value than oxygen does. So hydrogen is going to hold its electrons loosely. Does hydrogen attract electrons? We said no, because it has a lower electronegativity value. Does oxygen hold its electrons tightly or loosely? Well, since oxygen has a high electronegativity value, tightly will be our answer. And so does oxygen tend to attract electrons? Yep, it does, because it's got a higher electronegativity value. Since oxygen has a higher electronegativity value, electrons are going to spend more time around that atom. And therefore, since oxygen attracts electrons, which are negatively charged particles, then the part of the water molecule that will be more negative is oxygen, while the hydrogens will be more positive. Remember that intramolecular bonds, these are the bonds that occur inside of a molecule. They are ionic, nonpolar, covalent, or polar. They contribute to whether the molecule as a whole is polar or nonpolar. So when you look at this water molecule, you can see that the green shaded area, that's where the hydrogens are, that's a little bit more positive. Why? Because the blue part, the oxygen, is attracting electrons toward it. It's pulling the electrons away from hydrogen so that they spend more time around the oxygen, making the middle of the molecule more negative and leaving the outside more positive. Now, this is something that you guys have already done. These are electronegativity values, and you need to use them in order to determine what kind of bond exists between two atoms. And so basically, what you're doing is you're subtracting the values that you have here in the electronegativity table, and then you come down here and use that difference to figure out what kind of bond you have between two atoms. And so here, go ahead and pause this video so that you can figure out what the electronegativity difference is and what the intramolecular bond type is. All right, now that you have those answers, let's check them and see how you did. There you go. So for this one, especially between sodium and chlorine, this one you could just look at it and know that it's ionic because you have a metal and a nonmetal, and that automatically gives you an ionic bond. All right. Thank you very much. Enjoy the rest of your learning.